So far, we have seen that we can represent functions in the time domain and the frequency domain. Another way that we can look at signals is how to store them or how to transfer them from one place to another. So let's say we have a sinusoid over here. A sinusoid goes like this. Where its minus point is -3 and its highest point is at 3. This is our t-axis, and this function is described by the following formula: 3 times the cosine of 6 pi t minus pi. Well, let's say we want to store this function into a CD, because maybe it's music or maybe it's something else. Then the wave that we observe is our xt. Then, because this is in the continuous domain, we want to transfer it to a discrete function. And you can actually see this as an array with all values in it. And if we want to write it in a continuous form, it is just the n times the sampling period. What a sampling period is, I will talk about in a second. This is our discrete part, and then we want to go back to an output once again, which we denote with a tilde over our x, which is again in the continuous domain. Now, what was our sampling frequency or our sampling period? And that depends on the values that you choose. Once again, these two are related with the following functions, where the frequency is 1 over the sampling period and the sampling period is 1 over the sampling frequency. Our function of xt always looks like the following: a times the cosine of omega t plus phi. If we go to the discrete domain, our function changes because we fill in n times ts. So we get a times the cosine of omega times n times ts plus phi. And we call our omega multiplied with our sampling period omega hat. And omega hat just shows us or denotes what the frequency is times the sampling period. If we do that for our function, furthermore, we can reconstruct this, but that's for another video. If we do that for our function over here, then I'll give you the following values. Our sampling frequency is 12 Hertz. It gives us a sampling period of 1 over 12. Now for our function, we get 3 times the cosine of 6 pi times n times our sampling period, which was 1 over 12, minus pi. If we rewrite this a little bit, we get a half pi times n minus pi, where we see that our omega was 6 pi and our omega hat right now is 1 over 2 pi. And with this sampling, we can calculate what our discrete values will be. Because for n is 0, we of course fill that in. We get 3 times the cosine. This is of course different. We get 3 times the cosine of pi divided by 2, or half times pi, it's the same, times 0 minus pi. So that is 3 cosine, and pi divided by 2 times 0 is 0, so just of negative pi, which is equal to minus 3. For x of 1, we get 3 times the cosine of a pi divided by 2 times 1 minus pi, which gets us the cosine of minus a half pi, which is 0. So if we draw that already in our stem plot, or our function over here, we get these values so far. And if we do that for all the other values, for x0, x1, and then x2, x3, x4, etc., then we get all these nice data points of our function. And these data points, the height of our function, that is the value that is stored onto a disk or something else. We could have chosen a higher sampling frequency, and then we would have all the blue ones already, and then also the yellow ones. That is just another sampling frequency. And if you wonder, well, what is the most optimal sampling frequency, that we will talk about in the next video, because there we get to see Shannon's sampling theorem.